This will be the last video for this final exam study guide for Math 31B at UCLA for winter 2024. Okay, so we left off on 7. We aim to determine the convergence or divergence of this sequence. So part A, show that n factorial less than or equal to n to n minus 1 for n greater than or equal to 2. Hint, use the definition of the factorial. Okay, so this is actually pretty simple, and they even give you the hint. So what is n factorial? That's n minus 1, n minus 2, n minus 3, all the way down to 1. That's how factorials work. Like 4 factorial would be 4 times 3 times 2 times 1, because 4 minus 3 is 1, right? So it goes all the way down to 1. Okay, that's the right-hand side, less than or equal to n to the n minus 1 power. So that's just being n times n times n times n, all the way to, I don't know how many, but times n. So hopefully you can kind of see that obviously the left-hand side's smaller than the right-hand side, because the n's match the first terms, but starting from n, the second term, n minus 1 versus n, clearly this is smaller. N minus 2 versus n, clearly n minus 2 is smaller. N minus 3 versus n minus 3 is smaller. 1 versus n, 1 is smaller for n greater than or equal to 2. Okay? So, honestly, I would just say starting from n is equal to 2, the left-hand side less than equal to right-hand side, and that should be good enough. Okay, now part B. Determine the convergence or divergence of this sequence. You may use part A. Okay, well, so we want to take the limit as n goes to infinity, n factorial over n to the n. Okay, we just found that the n factorial is less than or equal to n to the n minus 1. So we can say when n approaches infinity, then n factorial is much less than n to the n minus 1. I should just write it here. I don't know why I didn't do that. Therefore, limit n goes to infinity, n factorial over n to n equals 0. It converges. It should equal to 0. Because as I was saying, you can imagine that when n gets very, very big, then n to the n. So it's the same thing. And it's just one less factor of n. Doesn't matter. So as I was saying, when n gets very big, since we already found that this is bigger, this is going to be much bigger. Like, if, for example, if n is like 1,000,000, for example, that's not even close to infinity, but that's a pretty big number. You're going to have 1,000,000 times 1,000,000 times 1,000,000 versus over here is like 1,000,000 times 1,000,000 minus 1 times 1,000,000 minus 2. And over here, it's going to be much bigger, clearly, hopefully, with that extreme-ish example. So if this is much bigger, then the limit will go to 0 because the denominator gets bigger and bigger, so it's going to go to 0. Convergence. Simple as that. Okay. And the last problem. Find the Taylor series about 0, aka the Maclaurin series, for f of x is xe to the minus x squared. Then find the 17th derivative of f at 0 and the 20th derivative of f at 0. Okay, so whenever you have something like this, we always start off with what the 3 Taylor series that we know. E, sine, and cosine. We know what e to the x is, so usually I just remember it by the expanded form. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial, so on and so forth. Okay, you can remember it by the summation notation too. This one's quite easy. N goes from 0 to infinity, x to n over n factorial. Okay? This is e to the x, so I'm going to work on this side, but you can directly work from here too. Totally fine. Okay, so we basically want to make this look like this. So we first can find e to the negative x squared. So wherever there's an x, we plug in negative x squared. So we 1 plus negative x squared plus negative x squared squared over 2 factorial plus negative x squared cubed over 3 factorial, so on and so forth. Okay, and we can simplify that a little bit. This is 1 minus x squared. This becomes plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial, so on and so forth. This is e to the minus x squared still. Okay, now we can multiply by x on both sides to make this match now. X e to the minus x squared, so we multiply x to every single term. X minus x cubed plus x to the 5th over 2 factorial minus x to the 7th over 3 factorial, so on and so forth. So we can write this in a closed form notation now. Okay? We got to recognize the patterns here. So as I said, you could have directly worked on this, but I like to just visualize everything that's going on, so I take the extra time to do it. Okay, so we are starting from, well, if we start from 0, and we're starting from x to the first power, and then this looks like it's odd powers, right? So we can write it as x to the 2n plus 1. That should work, because when n is 0, we get x to the first power. When n is 1, we get x cubed. When n is 2, we get x to the 5th, so on and so forth. That works for that. We have an alternating sign. We start from positive, so it should be like minus 1 to the n. Because when we start from n is 0, it's minus 1 to 0, which is 1, positive. N is 1, negative. N is 2, positive. N is 3, negative. Matches. Okay, how about this factorial? Well, this looks like it's 0 factorial, 1 factorial, 2 factorial, 3 factorial. So it's just n factorial. Okay, and this is part of your answer. That's the Taylor series, okay? We have also one like this, by the way. So you have, as I said, you could work directly from here. So wherever there's x, we do the same thing. Minus x squared instead. So it'll be summation. I'm going to drop the limits. It'll be minus x squared to the n power, okay, over n factorial. And then this is e to minus x squared is equal to this, okay? Now we have the x e to minus x squared. So we multiply by x everywhere. Well, by the way, we can rewrite this as minus 1 to the n, x to the 2n over n factorial. We add x to all the terms, so we're going to add 1 power to the x. And isn't that the exact same thing I got over here? So as I said, you can just work directly from the summation notation. That's totally fine. Or you can do it like this. I prefer to do it like this because I like to see what's going on. Okay, it's a little slower, but I think it's worth the time. Okay, 17th derivative at 0. Obviously, you don't want to keep taking derivatives 17 times. There has to be a quick way to do this. What is the quick way to do it? Well, this is a power series. That's the key. We have powers of x. Okay? So, when we take, for example, just one derivative, what happens? We get 1 minus 3x squared plus something x to the 4th power minus something x to the 6th power, so on and so forth. All these terms have x, so when we plug in x is 0, they will all go away. But we still have that 1 from the derivative of x. Okay, so similarly, when we take the third derivative, we will have some constant in front of here. It will be actually minus 3 factorial. Okay? And everything else would go away because they'll still have an x there. And when we plug in 0, everything would go away. Okay? So let me even show you a few examples of that. Okay? So as I said, f prime would be 1 minus 3x squared plus dots. When we plug in 0, all those would go away. We're left with 1. So like f triple prime, we would have, first of all, when we take the second derivative, so we had the first derivative here, it will be minus 3. Okay, let me do the second derivative first, just to illustrate. This would go away. We get minus 3 times 2. I'm writing like this on purpose. x plus dot dot dot. So f triple prime would be minus 3 times 2. Okay? This 3 times 2, notice, is 3 factorial because there's a missing 1 there. And similarly, it will be like that. So it will always be that power factorial, but this minus sign still is there, okay, from the original over here, okay? So when we have the 17th derivative, okay, we need the coefficient out in front of x to the 17th, okay? So it'll be 17 factorial times the existing coefficient out in front. Like over here, it was 3 factorial times the existing coefficient out in front, which was negative 1. Okay? And similarly over, even in this example, f prime, if we want f prime is 0, it will be 1 factorial times the existing coefficient out in front, which is 1. 1 times 1 is 1. Okay, so what's the existing coefficient out in front of x to the 17th? So how do we get x to the 17th? That's when n is equal to 8. So we would get 8 factorial on the bottom, okay? And minus 1 to the 8th power is positive, okay? So this is your answer. Hopefully that made sense. To recap one more time, when we keep taking derivatives, the power rule happens. So it's just n factorial. Like here it was just 1 and then 3 times 2. For the 5th power, it'll be 5x to the 4th, and then bring down the 4 next time, x to the cube, bring down the 3 next time, so that's 5 factorial if we take the 5th derivative. So similarly, 17th derivative, it'll be 17 factorial. But we still have to consider what was out in front already of the x to the 17th term. Like in this case, x to the 5th, we had to take the half, or if we took the 7th derivative, we need to take 1/6, because 3 factorial is 6, so when we have this minus sign, so we need to take the 1/6. Now, what was out in front initially in the 17th degree term? That's when n is equal to 8, because 16 plus 1 is 17. So when n is 8, we get x to the 17th. Down here, we get 8 factorial, that's what I put there. And minus 1 to the 8th power, that's just positive. So that's this answer. Okay, now what about the 20th derivative? Okay, so by the same logic, what's the coefficient out in front of the 20th degree term? Well, notice that it's all odd. So it would be, technically, it would be it'll be 20 factorial times 0. Because we have a 0 out in front of the x to the 20th term. So this is 0, as simple as that. Okay, that's how you solve these types of Taylor series problems. For some reason, they love asking this at UCLA. So this is how the technique to do it. Okay, this is the end of this study guide. Hopefully this series has been helpful. Please like and subscribe if it was.